So at the end of the last video, we talked about using polar coordinates to graph lines. There's going to be two different looking equations for lines that go through the origin and lines that don't. In this section, 9.7, we're looking at other kinds of curves using polar coordinates rather than rectangular coordinates, x and y's, that you're used to. So we're going to try to graph some polar equations by hand. Let's do one together. So the graph of an equation in two variables is the set of all ordered pairs satisfying the equation. That's true in rectangular coordinates. That's also true in polar coordinates. Except in polar coordinates, the first coordinate is r, the distance from the origin, and the second coordinate is theta, the angle from the positive x-axis. So to graph this polar equation, r squared equals 4 sine 2 theta, we're going to start by plotting some points. And by what I mean when I say we're going to plot some points, what I mean is you're going to plot some points. So go ahead and pause the video, choose some thetas, and calculate r's and plot those points. Again, there's page 702 has this polar grid. You can also draw one by hand. So pause the video, do some calculations, fill out the table. All right, welcome back. So here is a filled out table. So I have several ordered pairs here. I have 0, 0, the origin. When theta is pi over 4, my radius is going to be plus or minus 2. So that corresponds to this point for r being plus 2, or this point for r being minus 2. When theta is pi over 3, that's going to give me plus or minus 1.86, which is here and here. And likewise, for pi over 6, that's going to give me plus or minus 1.86. It gives me this point and this point. We got a bunch of points. Now, if these were graphs that you were used to seeing, you would know, like, connect dots and what general shape they would be in. And you might be tempted to connect them in a certain way, and that's not going to be the right way. So this is, if you want to think through it, so this is the graph for the function 4 sine 2x in rectangular chords, right? I plug in x, it gives me a y value. So what can this graph of 4 sine 2x tell us about the graph of the polar equation r squared 4 sine 2 theta? Well, the period of f is pi. So we only have to look at theta from 0 to pi. F of x is less than 0 for all x in the interval pi over 2 to pi. So we'll get non-real values of r if we try to evaluate the equation r squared 4 sine 2 theta. And the absolute value of r is less than or equal to 2 for all thetas. Why? Think about that for a minute. So, by symmetry, and assuming these are continuous functions or continuous equation, we know sine is continuous, so we can connect the dots in this way. This is what the graph of the equation r squared 4 sine 2 theta looks like. There it is. Ta-da! Oh, should we do another one? And by we, I mean you. Yes. Yes, we should. Here's one. R equals 2 cos 5 theta. Make a table, plot some points, have a look at the function y equals 2 cos 5x. Think about symmetry. And, well, talk with a friend if you can. If you can't talk with a friend, that's okay too. So pause the video, go ahead and give this plotting this equation a try.